What would be the very first thing to change if a black hole came near Earth? Not the day it arrived, not in a dramatic flash, but years before anyone noticed. Long before oceans stirred or skies darkened, would the universe leave quieter clues behind? Tonight's question isn't about destruction or fear. It's about detection, about subtle shifts in gravity, time, and motion that begin long before anything breaks. The kind of changes that don't scream for attention, but whisper patiently, waiting for someone to listen closely enough. Welcome back, traveler. Tonight we drift through science. You're lying in bed, maybe with the room mostly dark, the glow of a screen fading as your eyes grow heavier. The outside world has softened into distant hums and muted sounds. If you enjoy exploring these quiet scientific questions at night, the kind that don't rush you, you can like the video, subscribe, or leave a comment telling where you're listening from and what time it is right now, wherever you happen to be resting. If you're awake because sleep hasn't come easily, or because your thoughts keep circling tomorrow, you're exactly where you're allowed to be. There's no pressure here to stay alert or to understand everything perfectly. You don't need to track every explanation or remember every number. It's completely fine if your attention drifts, if images blur together, or if you fall asleep midway through a sentence. This isn't a lesson you're being tested on. It's a place to slow down. Tonight, we'll move gently between the vastness of space and the very human effort to understand it. We'll explore what gravity does when something extraordinarily dense comes closer, and how scientists have learned to notice these effects through telescopes, satellites, and long nights of correcting data that didn't behave as expected. Here on Orbit Sleep, we like to explore the universe not just as it is, but as humans slowly discover it through curiosity, mistakes, and patient observation. So take a moment to get comfortable. Let your breathing settle into a steady rhythm. You can dim the lights a little more, adjust your pillow, or close your eyes if that feels right. Tonight, we'll walk slowly through what truly happens when a black hole comes near Earth, starting with the quiet changes that arrive first, long before anyone realizes what's approaching. You don't need to stay awake for the whole journey. Just listen and let it unfold. You're still lying there, breathing quietly, while far above your ceiling, the universe continues its slow, indifferent motion. Imagine space not as empty, but as something soft and flexible, like a stretched fabric. You can't see it, but everything moves along its gentle curves. Tonight, nothing explodes, nothing screams. The first thing to change, if a black hole comes near Earth, is not light or matter, but the invisible shape of space itself, bending ever so slightly. Gravity isn't a force that reaches out and grabs. It's more like a quiet permission slip, telling objects how they're allowed to move. When something massive exists nearby, paths curve toward it naturally. A black hole doesn't pull harder than other objects of the same mass. That surprises many people. What makes it different is not strength bias, but concentration. The same mass squeezed into a much smaller volume. If a black hole with the mass of our sun replaced the sun itself, Earth would continue orbiting almost exactly as it does now. That sounds unsettling, but it's true. The orbital dance depends on mass, not on whether that mass shines. The difference would be darkness, not immediate destruction. This detail comes from centuries of gravitational math, refined through observations, not speculation. Scientists first realized gravity worked this way by watching planets, not black holes. Isaac Newton inferred it from planetary motion. Albert Einstein later refined it, describing gravity as curvature in space-time. That idea wasn't accepted easily. Early measurements didn't line up perfectly. Astronomers had to adjust calculations again and again, checking Mercury's orbit, correcting tiny mismatches that hinted something deeper was happening. You're still here in your bed while those corrections echo through history. Think of gravity like a slow river current beneath a calm surface. You don't notice it unless something drifts. If a black hole approached from far away, its influence would begin as a barely measurable change in trajectories. Asteroids, comets, even the distant orbits of outer planets responding first. Those changes would be extraordinarily small at first. A black hole 1 light-year away would have no noticeable effect on Earth. Even at 1/10 of a light-year, the influence would be subtle. Numbers matter here. A light-year is about 9 trillion kilometers. Gravity weakens with distance, fading quietly rather than snapping suddenly into danger. Astronomers detect these shifts using long-term observation. Telescopes like Gaia, operated by the European Space Agency, track stellar positions with astonishing precision. Gaia can notice a star wobble by microseconds, movements equivalent to seeing a coin shift on the moon. That's how humans learn to listen to gravity's whispers. In labs and control rooms, scientists don't see black holes directly. They see spreadsheets, graphs, residuals that don't behave, a star slightly off schedule, a comet arriving a fraction early. These anomalies spark debate. Is it an error, instrument drift, or something unseen? Most of the time, it's noise. Sometimes, it's discovery. Imagine gravity as a clock that ticks differently depending on where you stand. Near massive objects, time slows slightly. This has been measured near Earth itself using atomic clocks on satellites. GPS systems must correct for this difference daily. If they didn't, navigation would drift kilometers off course within hours. A nearby black hole would exaggerate this effect, but gently at first. Clocks closer to its influence would fall behind imperceptibly. No one would feel it. No one would age faster or slower in any meaningful sense. But the math would notice. Equations would stop agreeing with expectation. While you lie there, wrapped in warmth, space would be doing something similar, adjusting, settling into a new balance. Gravity refuses to announce itself. It alters permission, not sensation. That's why the first warnings wouldn't come from earthquakes or tides, but from patient data sets accumulating over years. Human history is full of moments where data whispered before reality shouted. Neptune was discovered because Uranus didn't behave properly. Astronomers noticed deviations, argued, recalculated, and finally predicted an unseen planet. When telescopes turned to the right place, there it was. Gravity had spoken long before sight confirmed it. A black hole's approach would follow the same pattern. Orbits would stretch, compress, tilt by tiny angles. The outer solar system would feel it first. The Oort cloud disturbed, sending comets inward centuries later. Cause and effect move slowly in space. You don't need to hold all these mechanics in your mind. Let them drift like shapes behind your eyelids. The key idea is simple. The universe warns quietly. It prefers patience over panic. The most dangerous changes are often the calmest ones at the start. There's something oddly comforting about that. Even cosmic threats don't rush. They arrive gradually, obeying rules older than fear. While your breath slows, gravity continues its careful accounting, keeping track of every mass, every distance, every permission to move. You're not meant to react to this information tonight. Just notice how distant it feels, how removed from your body, your room, your worries. The universe can rearrange itself on unimaginable scales, and still, you remain here, supported by a mattress and a steady inhale. As this subtle reshaping unfolds far away, something even stranger begins to happen. Not in space, but in how motion itself behaves. And while gravity quietly redraws its maps, the sky starts preparing changes that no one sees coming yet. For now, nothing dramatic happens. That's the most honest beginning. And if you're somehow still awake at this point, still listening, still curious, you're exactly the kind of person this channel is for. You can subscribe if you'd like. No pressure. Gravity will keep doing its thing either way, and we'll keep telling the story. You're still lying there, barely moving, while far beyond the atmosphere something begins to drift out of alignment. Not dramatically. Not enough for anyone to point at the sky in panic. Just enough that, over time, the stars no longer return to quite the same places they used to. The constellations you recognize stay familiar, but their geometry starts to soften, like a memory recalled a little differently each time. To the naked eye, nothing changes at first. The night sky feels eternal because it changes so slowly. But precision instruments don't share that illusion. When a massive object like a black hole comes closer, it subtly bends the paths of light, traveling near it. This effect is called gravitational lensing, and it means starlight arrives slightly shifted from where it should be. The numbers involved are tiny. Light passing near a strong gravitational field can bend by fractions of a degree, sometimes by microarcseconds. That's smaller than what your eyes could ever resolve. But modern astronomy doesn't rely on eyesight. It relies on detectors chilled near absolute zero, measuring photons one by one as they arrive after journeys lasting thousands or millions of years. Imagine a star that has always appeared in the same spot, night after night, generation after generation. Suddenly, over years of careful measurement, it seems to wander. Not randomly, consistently, slowly, as if space itself has been gently nudged. This wouldn't feel like a threat. It would feel like a puzzle. This is how black holes are often found in the first place, not by seeing them, but by noticing what they disturb. Astronomers have discovered black holes by tracking stars near the center of our galaxy, watching them whip around something invisible. Those stars move at thousands of kilometers per second, responding to a mass that emits no light at all. The European Southern Observatory spent decades watching stars orbit Sagittarius A, the supermassive black hole at the Milky Way's core. The breakthrough couldn't come from a single image, but from patience. Years of data, repeated nights, tiny corrections, proof that the universe reveals itself slowly if you're willing to wait. You're still here, listening, while that same patience would be required closer to home. If a black hole were approaching our solar neighborhood, astronomers wouldn't announce it suddenly. They would argue first about calibration, about noise, about whether a detector had drifted or a model needed adjustment. In control rooms, this looks very ordinary. Coffee cups, screens filled with plots, someone pointing at a line that curves when it shouldn't, someone else saying, "That's probably nothing." Science advances through skepticism long before certainty. Light behaves strangely near massive objects. Paths curve, time stretches, frequencies shift. This is why distant galaxies sometimes appear stretched into arcs around massive clusters. The light hasn't changed. Space has. A nearby black hole would create a similar, though far subtler, effect across the sky. You might imagine the stars trembling, but that's not how it happens. Instead, catalogs stop agreeing with themselves. A star listed at one coordinate no longer matches newer observations. The discrepancy is tiny, but persistent. Enough to survive Arabarv, enough to make someone uneasy. The Gaia mission has mapped over 1 billion stars in our galaxy, measuring their positions and motions with unprecedented accuracy. Gaia's data is so precise that even the gravitational pull of distant structures leaves fingerprints. If something massive wandered closer, Gaia would notice long before humans ever could. While you rest, the sky would be quietly betraying its secret. Not with flashes or streaks, but with spreadsheets refusing to settle, with models that fit yesterday but fail today. This is how the universe clears its throat. There's a poetic unfairness to this. The most profound changes are invisible to the people living through them. The sky looks the same, the stars still sparkle, and yet, deep down, the math no longer balances. Black holes don't announce themselves. They distort, they persuade. They bend paths until nothing quite lines up the way it used to. And the universe allows this without drama, as if it has all the time in the world, because it does. You don't need to picture every arc or equation. Just imagine a familiar map slowly warping, like paper exposed to moisture. No tearing, no burning. Just gentle deformation that accumulates until it can't be ignored. As you breathe, steady and slow, remember that light reaching your eyes tonight has already traveled through curved space. This is normal. It's happening all the time. A nearby black hole would only make this quiet truth slightly louder. Still, nothing feels wrong on Earth. No alarms, no shaking ground. Just astronomers feeling that something somewhere is pulling the sky ever so slightly out of place. And while the heavens begin to misalign, something closer to home starts to react as well. Not in light, but in motion. Because when gravity redraws space, everything that moves must reconsider its path. Far from the glow of cities and screens, motion itself starts to feel slightly less obedient. Not here, not yet, but out where distances are measured in billions of kilometers, and patience is a requirement. Objects that once followed predictable paths begin to trace lines that are just a little off, like handwriting that has slowly changed over the years without anyone noticing. Planets move because they're allowed to. An orbit is a negotiation between forward motion and gravitational pull, a balance that usually holds steady for millions of years. When an extra mass enters the conversation, especially one as dense as a black hole, that balance doesn't break, it adjusts. The first places to feel this adjustment wouldn't be Earth or Mars, but the distant edges of the solar system. Beyond Neptune lies the Kuiper Belt, and farther still, the Oort cloud, a vast spherical halo of icy debris extending nearly a light year from the Sun. These regions are only loosely bound. Their orbits are fragile. A passing gravitational influence would gently tug on these distant objects, altering trajectories so slightly they'd take centuries to fully reveal themselves. Some comets would be nudged inward. Others would be flung away. From Earth's perspective, this would look like coincidence at first, an unusual increase in long-period comets arriving from unexpected directions. This isn't speculation. Astronomers already use comet behavior as a clue to unseen influences. Patterns matter, direction matters, timing matters. When those patterns shift together, scientists start asking what changed in the gravitational environment. Back in observatories, this discovery wouldn't arrive with certainty. It would arrive as discomfort, as a model that predicts 10 comets but observes 14, as a distribution that should be isotropic but isn't. Someone would rerun the code. Someone else would double-check the input data. Orbital mechanics is unforgiving. Small forces, applied over long times, produce large outcomes. A difference of millimeters per second today can mean millions of kilometers centuries from now. This is why space agencies obsess over decimals. This is why navigation errors compound quietly until they don't. Imagine standing on a slowly turning carousel. At first, the motion feels smooth, but if someone adds weight unevenly, the rhythm changes. Not abruptly, just enough that your inner sense of balance notices before your eyes do. That's what gravity does to orbital systems. You're still resting there, unaware of these distant negotiations. while objects the size of mountains begin taking slightly altered routes through space. No one feels threatened. No one feels warned. The solar system simply becomes a little less symmetrical. When scientists simulate these scenarios, they don't model explosions. They model probabilities. They run thousands of simulations, nudging parameters, watching how orbits stretch and precess. Most runs look harmless. A few don't. That's what makes the exercise unsettling. In one simulation, a distant comet becomes an Earth-crossing object thousands of years later. In another, a planet's orbit becomes more elliptical, changing its climate over epochs. None of this happens quickly. Gravity prefers long games. These simulations are done in quiet rooms, on machines humming softly, often overnight. Researchers come back in the morning to results they half expected and half feared. The universe doesn't care if anyone is watching. It just keeps integrating forward. What's remarkable is how stable the solar system usually is. For billions of years, the planets have kept roughly the same paths. That stability is a kind of cosmic kindness. A nearby black hole wouldn't shatter it, but it would test it. You don't need to picture the equations behind this. Just imagine paths gently reshaped, like grooves in sand after the tide shifts. The lines remain, but their curvature tells a new story. Closer in, planets would remain calm for a long time. Earth's orbit might become slightly more oval. The year might lengthen or shorten by minutes. Seasons would drift slowly. Nothing you'd notice in a lifetime, but astronomers would. Atomic clocks would. Long-term data sets would. Humanity's habit of measuring everything eventually catches even the quietest changes. There's something humbling about that. The universe can alter the choreography of entire worlds without raising its voice. And humans, tiny as they are, have learned to note this anyway. Not through instinct, but through persistence. While you lie there, breathing evenly, remember that motion is never guaranteed. It's always conditional, always responding to what's nearby, even if nearby means across incomprehensible distances. As orbits slowly begin to forget their old shapes, another effect starts to layer on top of everything. Not about where things move, but about how fast time itself flows along those paths. Time doesn't announce itself when it changes. It doesn't slow with a sound or speed up with a warning. Instead, it quietly disagrees with expectations. Somewhere far above your roof, while your breathing stays steady, time would begin to flow at slightly different rates depending on where you are and what's nearby. Most people imagine time as uniform, a shared river everyone floats along together. Physics disagrees. According to Einstein's relativity, time bends in the presence of mass. The stronger the gravity, the slower time passes. This isn't philosophy. It's measurement. It's something engineers account for every day. Even here on Earth, time doesn't tick evenly. Clocks at sea level run slightly slower than clocks on mountaintops. Satellites experience time differently than receivers on the ground. GPS systems must correct for this constantly. Without those corrections, your phone's location would drift by kilometers in a single day. A nearby black hole wouldn't create cinematic time distortion, at least not at first. Instead, it would introduce tiny disagreements between clocks placed at different positions in the solar system. No one would feel dizzy, no one would sense delay, but the numbers would stop lining up. Atomic clocks are among humanity's most precise creations. They can measure time to within billionths of a second. When two such clocks disagree consistently, something fundamental is happening. This is how relativity stopped being theoretical and became practical. Imagine a network of clocks spread across space, on Earth, on satellites, on distant probes. As a massive object approaches, those clocks begin to drift relative to one another, not randomly, Predictably, following equations written long before the instruments existed, in labs, this looks deceptively boring. Rows of timestamps, residuals plotted against models, someone noticing that corrections keep getting larger instead of smaller, someone else suggesting a systematic error. They always do, at first. You're still lying there, insulated from all of this while engineers argue about nanoseconds. It's strange how cosmic events express themselves first as paperwork and doubt rather than sensation. Time dilation isn't dramatic until gravity becomes extreme. Near a black hole's event horizon, time nearly stops relative to distant observers. But long before that, long before anything dangerous, subtle gradients appear. Time stretches unevenly, like elastic pulled more on one side than the other. This stretching would affect orbital dynamics too. Objects don't just move through space, they move through space-time. Change the tempo, and the dance shifts. Periods lengthen. Frequencies drift. Resonances weaken or strengthen. Space agencies already monitor these effects. Missions like the Deep Space Atomic Clock experiment were designed to test how well we can track time far from Earth. Precision timing isn't luxury. It's navigation. It's survival. There's something poetic about discovering danger through patience. Not through alarms, but through discrepancies that refuse to disappear. The universe doesn't rush its messages. It lets them accumulate. Think of time like a song playing at slightly different speeds in different rooms. At first, no one notices, but when the doors open, the mismatch becomes undeniable. That's what gravity does to time. It desynchronizes reality. You don't need to imagine clocks exploding or seconds stretching visibly. Just picture alignment slowly failing, schedules drifting, predictions missing by margins too large to ignore, too small to fear. Astronomers would begin asking uncomfortable questions. Not what is coming, but what assumption no longer holds. Science rarely jumps to cosmic conclusions. It eliminates human error first. But eventually, elimination runs out. Instruments agree with each other. Data converges. And what remains is not noise, but a signature. Mass affecting time across vast distances. While all this unfolds, Earth remains calm. Days feel the same length. Nights still come. Your body keeps its rhythm. Biology is forgiving of tiny temporal changes. That contrast is unsettling in a quiet way. The universe can alter its deepest structure without interrupting dinner, sleep, or breath. Reality doesn't need to be loud to be different. You're allowed to let this idea fade into the background now. Let it become texture rather than focus. Time is doing strange things elsewhere, but here it's only asking you to rest. As space-time subtly retunes itself, another consequence begins to emerge, not in clocks or orbits, but in energy itself, as radiation and matter respond to a shifting gravitational landscape. Long before anything looks wrong, energy begins to take slightly different paths. Not dramatically, not violently, just enough to confuse expectations. Photons, particles of light that usually travel obediently across space, start arriving with energies that don't quite match predictions. To most of the universe, this is normal. To scientists, it's a raised eyebrow. Light climbing out of a gravitational field loses energy. This is called gravitational redshift. It's been measured countless times, from light escaping the sun to signals sent from spacecraft near massive planets. When gravity changes locally, the color and frequency of light adjust accordingly, sliding gently toward longer wavelengths. Instruments designed to monitor cosmic radiation would be the first to notice. Space-based observatories track gamma rays, X-rays, and high-energy particles arriving from distant sources. These detectors are tuned carefully, calibrated obsessively. When patterns shift without explanation, they stand out. A nearby black hole wouldn't suddenly flood Earth with radiation. Black holes are dark. They emit nothing unless actively feeding, but their gravity affects everything passing nearby. Radiation traveling through warped space-time changes its behavior, not louder but different. Imagine light as a stream flowing downhill. Change the slope and the speed adjusts, not abruptly, gradually. That's how gravitational fields shape energy. A black hole approaching would introduce new gradients, altering how radiation propagates through the solar system. Back on Earth, scientists would compare notes. A telescope in orbit notices a spectral shift. A ground-based detector confirms it. Someone suggests solar activity. Someone else pulls solar data and shakes their head. The sun is behaving normally. This is where the human side of science becomes visible. Emails fly. Video calls happen late at night. People recheck assumptions. Models are updated. Most explanations fail. That's when curiosity deepens. Cosmic rays, high-energy particles constantly bombarding Earth, would also respond. Their trajectories bend under gravitational influence. Subtle changes in arrival direction and energy distribution would appear. Again, not enough to alarm, but enough to intrigue. These particles have been studied for over a century. Instruments buried deep underground or high in the atmosphere count them patiently. When long-term statistics drift, it means something upstream has changed. You're still resting, while all this manifests as quiet deviations in charts. Nothing about your room changes. The same shadows, the same temperature. Meanwhile, energy itself is being slightly rerouted by an invisible presence. There's a strange elegance to this. The universe doesn't need to break rules to signal change. It just applies them consistently in new conditions. Physics remains calm, even when outcomes feel unsettling. Gravitational fields also affect vacuum fluctuations, the constant, low-level activity of empty space itself. While this remains deeply theoretical, experiments already show that energy behaves differently near massive objects. Nothing mystical, just complexity. Scientists working on detectors like LIGO are used to separating signal from noise. They've learned that the universe whispers far more often than it shouts. A nearby black hole wouldn't scream into their instruments. It would murmur. That murmuring would grow slowly louder. More data points drifting, more corrections required. The sense that something is shaping the environment in ways models didn't anticipate. You don't need to visualize equations or spectra. Just imagine a room where the air pressure changes slightly. You don't notice immediately, but instruments do, and eventually so do you. There's comfort in knowing this happens gradually. The cosmos is patient. It allows time for observation, discussion, and understanding. Even massive objects follow etiquette. While energy shifts invisibly around Earth, another layer of reality begins responding as well. Not light, not time, but matter itself, starting with the most delicate structures in space. Out where the solar system thins into sparsity, matter exists in its most patient form. Dust grains drift for millions of years without touching anything. Wisps of gas spread so thin, they would pass unnoticed through your room. This is the first kind of matter to respond when gravity changes its tone. Unlike planets or moons, dust and gas don't have the comfort of momentum or mass to resist disruption. They are easily persuaded. A slight curvature in space-time is enough to redirect them, to gather them, or to stretch them into filaments that trace invisible forces. Interplanetary dust already responds to gravity from planets and the sun. Its motion creates faint phenomena, like zodiacal light, a soft glow seen before sunrise or after sunset. caused by sunlight scattering off dust in the inner solar system. A new gravitational influence would subtly reshape this glow. Gas behaves similarly, but more dramatically. Clouds of hydrogen and helium between planets and stars are constantly responding to gravitational fields. They compress, expand, and drift in response to changes that solid bodies barely notice. A nearby black hole wouldn't suck this material inward like a vacuum cleaner. Instead, it would begin reorganizing it. Density gradients would shift, streams would form. Regions that were once quiet would slowly become structured. Astronomers already study this process around black holes in distant galaxies. They see gas heated, stretched, and sometimes accelerated into luminous disks. Those are extreme cases. What we're imagining here is quieter, the very first whisper of reorganization. In simulations, dust responds first because it has the least inertia. Small changes accumulate quickly. A grain nudge today ends up far from its original path centuries later. Multiply that by trillions of particles, and the environment slowly changes character. These changes wouldn't be visible to your eyes. They'd show up in infrared data, in polarization measurements, in faint emissions barely rising above background noise. This is where astronomy becomes an art of patience. In research facilities, scientists studying dust and gas work with data that looks almost empty, low signal, high uncertainty. They learn to trust statistics rather than images, to believe patterns before believing pictures. You're still resting while this happens. While space fills with gentle rearrangements, nothing crashes, nothing collapses. Matter simply starts obeying a slightly different geometry. There's something deeply non-threatening about this stage. Matter doesn't panic. It adapts. It flows where curvature allows, collecting where gravity suggests. The universe isn't violent by default, it's responsive. Dust grains collide softly. Gas cools and warms. Filaments stretch like slow-moving smoke. These processes take place on timescales that make human urgency irrelevant. Yet these changes matter. Dust and gas are the scaffolding of future structures. Alter them, and you alter what may form later. Comets, clouds, even stars, given enough time. Astronomers would begin noticing subtle asymmetries. Emission lines slightly skewed. Dust clouds thicker on one side of a region than the other. Again, nothing definitive. Just persistent. The challenge here is belief. When does a pattern stop being coincidence and start being evidence? Science advances when enough independent observers see the same quiet thing. Think of matter as a chorus that only sings when gravity cues it. Change the cue, and the harmony shifts, slowly, gently, without a conductor's baton. You don't need to follow every implication. Let the image remain soft. Matter responding like breath to posture, automatic, unconscious, inevitable. As fragile structures adjust, more robust systems begin to feel the influence too. The story moves inward now, toward larger bodies that take longer to persuade, but cannot ignore gravity forever. Long before anyone looks to the sky for answers, the oceans begin doing what they've always done, rising and falling in quiet obedience to gravity. From the shore, nothing seems unusual. Waves break, tides come in and out, but the timing begins to drift, just slightly, like a familiar song played a fraction of tempo. Tides exist because gravity isn't uniform. The moon pulls more strongly on the near side of Earth than the far side, stretching the oceans into subtle bulges. The sun adds its own influence. Together, they choreograph a rhythm that's been stable for millions of years. Introduce another massive object into the neighborhood, and that rhythm doesn't collapse, it recalibrates. The black hole's gravity would be weak at first, but not irrelevant. Its pull would add a third voice to the tidal conversation. The effect would be tiny, measured in millimeters, seconds, fractions of a percent. No coastal flooding, no rogue waves, just deviations that instruments, not instincts, would notice first. Tide gauges around the world already record sea levels continuously. They were designed to track climate change, storms, and tectonic motion. But they also reveal gravitational patterns. When those patterns drift consistently, scientists start asking why. You're still lying there, unaware that the oceans are slightly out of sync with their own memory. Water doesn't complain, it responds. It redistributes energy until balance is restored. Lunar motion would also begin to show changes. The moon's orbit is incredibly well understood. Laser ranging experiments bounce light off reflectors left on a lunar surface decades ago. These measurements track the moon's distance to millimeter precision. A nearby black hole would subtly alter that orbit, not by dragging the moon away, but by changing the gravitational context in which the Earth-Moon system exists. Orbital precession would shift, timing would drift. In labs analyzing this data, the first reaction would be disbelief. The moon is reliable. It's the baseline. When the baseline moves, confidence is shaken. But gravity doesn't care about comfort. It treats all mass equally. Systems nested within larger systems inherit the influences of everything around them. Think of it like carrying a cup of water while walking on a moving platform. The water doesn't spill, but its surface adjusts to forces you barely feel. That's what the oceans and the moon would be doing. Tidal friction also affects Earth's rotation. Over long periods, tides slow the planet's spin. Days lengthen by milliseconds per century. This is already happening. A new gravitational influence would slightly modify that rate. You wouldn't notice days getting longer. Your circadian rhythm wouldn't care. But atomic clocks would. Astronomers would. Timekeeping agencies already insert leap seconds to correct for Earth's changing rotation. It's strange to realize how many layers of stability depend on gravity staying predictable. When it doesn't, adjustments ripple outward quietly, touching systems that feel timeless. The comforting part is this: these changes unfold slowly. Oceans don't panic. Moons don't fall. Everything adapts at the pace physics allows. While you rest, wrapped in stillness, entire planetary systems are negotiating balance without urgency. The universe is very good at that. As tides listen and respond, another consequence begins to rise, not in water or motion, but in the deep interior of planets themselves, where stress accumulates silently over time. Deep beneath continents and oceans, long before anything cracks or shifts, planets carry quiet tension. Earth is not solid in the way stone feels solid. It flexes. Its mantle flows slowly, its core churns, and its crust floats like a thin shell over restless layers. These internal motions respond to gravity just as much as oceans and orbits do, only on longer, quieter timescales. When gravity changes its background conditions, stress redistributes, not suddenly, not violently, but persistently. A nearby massive object would slightly alter how forces are balanced inside a planet. Pressures would shift by tiny amounts, almost impossible to isolate from normal geological noise, yet real all the same. Earth already experiences tidal stress from the moon and the sun. This stress doesn't just move water, it subtly flexes the crust itself. The planet expands and contracts by centimeters each day, like a slow breath. Instruments called strain meters record this motion continuously. Add another gravitational influence, and the pattern of that breathing changes. The amplitude remains small, but the timing shifts. Stress concentrates in slightly different regions. Faults that were stable remain stable, but their margins adjust. No one would feel this. Earthquakes would not suddenly increase. Volcanoes would not awaken en masse. The planet is far too large and resilient for that. But deep inside, energy would be redistributed, stored differently than before. Geophysicists already struggle to separate gravitational effects from tectonic ones. Earth is noisy. Plates grind. Magma moves. Water loads coastlines seasonally. Against this background, a black hole's influence would be subtle enough to hide for decades. Yet data accumulates. Over time, correlations emerge. Strain patterns repeat with unexpected periodicity. Models that once predicted stress relief fail slightly more often. These discrepancies don't scream danger. They whisper revision. You're still lying there, supported by a planet that feels immovable, while that same planet quietly negotiates forces on a scale your body will never sense. The mattress beneath you feels solid, but even it compresses under your weight. Solidity is always relative. In the laboratory, this shows up as long-term datasets that don't quite converge, seismic noise with unexplained modulation, variations in Earth's normal modes, the way the planet rings after large earthquakes, shifting by tiny margins. Earth has been described as a bell that rings when struck. Its tones are well cataloged. Change the gravitational environment, and the tuning shifts imperceptibly. The bell still rings, but not quite the same way. None of this is catastrophic. That's important. Planetary interiors are slow to respond. They absorb change gradually, like thick clay adjusting under steady pressure rather than snapping. This slowness is what makes detection so difficult. Humans prefer fast signals. Earth prefers patience. The mismatch creates long periods of uncertainty where nothing seems wrong, yet assumptions quietly expire. There's something calming about that scale. Even when influenced by something as extreme as a black hole, planets do not panic. They redistribute, adapt, and continue. You don't need to picture molten rock or shifting plates. Just imagine weight shifting in a deep structure, settling into a new equilibrium without drama. Gravity is not a hammer here. It's a suggestion applied consistently over time. As internal stresses subtly reorganize, another system tied closely to Earth begins to respond as well. The delicate shield that protects the surface from space itself. The atmosphere, bound loosely compared to rock or water, is sensitive to changes in gravity and energy flow. It doesn't notice first, but when it does, the signal becomes easier to see. While Earth adjusts inwardly, the space above it prepares for its own quiet response, shaped not by pressure or stone, but by charged particles and invisible fields. Above the surface you walk on, above oceans and clouds, Earth carries an invisible structure that never truly rests. The magnetic field stretches far into space, wrapping the planet in a teardrop-shaped cocoon called the magnetosphere. You never feel it directly, but it quietly deflects charged particles from the sun, guiding them away from the atmosphere like a steady, patient hand. This field is generated deep inside the planet, where molten iron moves within the outer core. Rotation, heat, and convection combine to produce currents, and those currents create magnetism. It's a delicate balance, sustained over billions of years, sensitive to both internal dynamics and external pressure. When gravity changes its background conditions, that balance adjusts, not dramatically, not in a way that flips poles overnight, but subtly enough to alter flow patterns inside the core. The effect is indirect, filtered through pressure, rotation, and time. Earth's magnetic field already changes naturally. It weakens, strengthens, drifts. Magnetic poles wander kilometers each year. Satellites constantly map these changes because navigation systems depend on them. The field is stable, but not fixed. A nearby massive object would slightly reshape Earth's orbital environment, and with it, the stresses and angular momentum affecting the core. Over long timescales, this could introduce small changes in how magnetic field lines organize themselves in space. You wouldn't see this by looking north. Compasses wouldn't suddenly fail, but magnetometers in orbit would begin noticing shifts in field strength and orientation that don't quite fit expected models. In space weather monitoring centers, this would show up as anomalies. Variations in how the magnetosphere responds to solar wind, changes in how charged particles are trapped and released. Again, not alarming, just persistent. The magnetosphere acts like a sail pressed constantly by solar particles. Change the gravitational context even slightly, and the shape of that sail changes. Compression on one side, stretching on the other. The shield still works, but its geometry evolves. The atmosphere sits just inside this shield, held by gravity, protected by magnetism. It's thinner than most people imagine, a fragile layer wrapped around a rocky world. Gravity determines how tightly it's held. Magnetism helps decide how much is stripped away over time. A stronger or weaker gravitational influence wouldn't cause the atmosphere to escape suddenly. Earth's gravity is more than sufficient to keep it bound. But subtle changes in upper atmospheric density and behavior would occur. Satellites already measure this. The upper atmosphere expands and contracts. Those upper layers would respond slightly differently. Not by rising or falling dramatically, but by redistributing density in ways that affect satellite orbits over years. Engineers would notice this first. Spacecraft experiencing more drag than predicted, or less. Orbital decay rates drifting from forecasts. Corrections accumulating instead of canceling out. You're still resting while all of this takes the form of spreadsheets and adjustment factors. No alarms, no headlines. Just more footnotes in mission planning documents. Auroras might change too suddenly. Not brighter storms, but shifts in where they appear and how they evolve over long periods. The interaction between solar wind and Earth's magnetic field is exquisitely sensitive. There's something humbling about realizing how many systems quietly protect life without ever being noticed. Gravity holds the air. Magnetism deflects radiation. Neither asks for attention. A black hole approaching doesn't strip these protections away. It nudges them. It changes boundary conditions, not rules. The shield remains, but it listens. You don't need to track every mechanism here. Just let the image settle. Earth wrapped in invisible fields, adjusting posture slightly as the cosmic environment shifts around it. And while the planet's defenses adapt patiently, something much more human begins to respond. Not in the sky or the ground, but in the instruments and minds of the people watching all of this unfold. At first, no one feels like they're part of something bigger. Each anomaly arrives alone, wrapped in its own context. A satellite behaving slightly differently. A data set that refuses to converge. A correction factor growing instead of shrinking. Individually, these things are unremarkable. Together, they begin to lean toward meaning. Science doesn't react with instinct. It reacts with meetings, conferences, emails written carefully to avoid sounding dramatic. Researchers are trained to distrust their own excitement, to assume error before explanation. That habit slows discovery, but it also protects it. A planetary scientist notices orbital drift. A physicist flags timing discrepancies. A space weather team reports unexpected magnetospheric behavior. None of them suspect a black hole. Not yet. The word itself feels too heavy, too cinematic. Instead, people start sharing data, informally at first. Have you seen something like this? Screens are shared. Graphs overlap. Patterns emerge that don't belong to any single discipline. This is where modern science becomes powerful, not in individual brilliance, but in aggregation. Data from ESA meets data from NASA. Ground-based observatories cross-check satellite records. Independent instruments tell the same quiet story. You're still lying there, perhaps drifting in and out, while human networks wake up. Not with fear, but with curiosity sharpened by consistency. Something is affecting gravity, time, radiation, matter, and fields all at once. Statisticians are brought in. Modelers build new simulations. Old assumptions are loosened. Hypotheses are tested and discarded. Most explanations fail quickly. That's normal. Elimination is progress. Eventually, someone suggests something extreme, not as a claim, but as a placeholder. A massive, compact object. Something dark. Something that doesn't emit, but influences everything nearby. The room goes quiet. No one wants to say it aloud yet. The idea isn't new. Black holes have been part of physics for over a century. But proximity is different from theory. Proximity makes abstraction uncomfortable. Still, caution dominates. A black hole near Earth would be extraordinary. Extraordinary claims require extraordinary evidence. The burden is heavy, and everyone knows it. Simulations are refined. Parameter spaces expanded. If such an object existed at various distances, would the observed anomalies match? Some runs begin to look uncomfortably good. You don't hear about this on the news. There's nothing to report yet. Uncertainty is not a headline, and scientists are acutely aware of the damage premature announcements can cause. Inside research institutions, tone remains controlled. Language stays dry. Words like suggests, may, and requires further investigation carry the weight of restraint. What's happening is not panic. It's convergence. Independent lines of evidence bending toward the same explanation, slowly enough to resist hype. This process takes years. Careers pass. Students graduate. Papers are revised and resubmitted. The universe does not rush human understanding. There's something deeply human in this phase, the willingness to sit with uncertainty rather than fill it with fear, to let data speak, even when the implications are uncomfortable. While you rest, humanity inches closer to realizing that the cosmic environment itself may be changing, not suddenly, but undeniably. And as recognition begins to solidify, a new question rises quietly beneath everything else. If something is out there, how close is it actually coming? Once suspicion begins to settle into something more concrete, the next question is unavoidable and deeply uncomfortable. How far away is it? Distance in space is never a simple measurement. You don't stretch a ruler between objects separated by light years. You infer. You triangulate. You listen to how gravity whispers across time. Astronomers have learned to measure distance by watching motion rather than objects. Parallax, for example, uses Earth's orbit as a baseline. As the planet moves around the sun, nearby stars shift slightly against distant backgrounds. The angle is tiny, but precise instruments can turn that shift into distance. For something invisible, though, parallax alone isn't enough. Instead, scientists rely on influence. How strongly does this unseen math bend paths, stretch time, distort radiation, and reorganize motion? Each effect carries information. Together, they form a fingerprint. Gravity doesn't hide its math well. It announces mass and distance whether it wants to or not. One of the first tools brought to bear would be orbital residual analysis. Planets, moons, and spacecraft all follow predicted paths based on known forces. When observations consistently drift from those predictions, the size of the deviation tells you something about how massive the unseen influence must be, and how far away it likely sits. This process is slow because precision matters more than speed. A miscalculation by even a fraction can change estimates by astronomical units. Teams run simulations across massive parameter spaces, asking the same question again and again. At what distance does this mass produce exactly these effects, and no others? Distance and mass are entangled in gravity. A very massive object far away can produce the same influence as a smaller object closer in. Untangling that requires multiple, independent signals. Timing discrepancies, orbital distortions, lensing effects, and energy shifts all respond differently to distance. Light bending, for example, falls off sharply with distance. Orbital perturbations behave differently. Time dilation gradients add another layer. By combining these, scientists slowly constrain the possibilities. The range narrows, uncertainty shrinks. This isn't done in dramatic control rooms. It happens in quiet offices, over months, with whiteboards filled and erased repeatedly. Researchers argue not about conclusions, but about error bars. How confident is confident enough to say anything at all? Eventually, a consensus range begins to emerge. Not a pointui, but a shell of probability. Something massive, compact, and dark appears to be influencing the solar system from far beyond the outer planets, but well within the sun's broader gravitational neighborhood. At this stage, time becomes part of the equation. Gravity propagates at the speed of light. What's being felt now reflects where the object was years ago, not where it is at this exact moment. Distance estimates must account for motion, not just position. Astrophysicists model trajectories. They ask whether the object is bound to the sun, passing through, or simply drifting by as part of the galaxy's background population. Each scenario implies a different future. If it's unbound, it came from elsewhere in the Milky Way, a rogue remnant of a collapsed star, wandering for billions of years before brushing past our system. These objects are thought to be common, though detecting them is rare. Simulations suggest there could be millions of stellar mass black holes drifting invisibly through the galaxy. Most never come near anything interesting. Proximity, not existence, is what changes everything. As distance estimates tighten, timescales stretch. Even a black hole moving hundreds of kilometers per second takes centuries to cross interstellar distances. This is not an incoming asteroid. It's not even a comet. It's a slow cosmic neighbor passing through. That realization changes the emotional texture of the discovery. Urgency dissolves. In its place comes something quieter, long-term awareness. Humanity would not be facing an imminent event, but a prolonged condition. Scientists are used to this. Climate change, stellar evolution, orbital decay, these are processes that outlast news cycles and careers. A nearby black hole would join that category, a reality to be studied, not reacted to. Communication becomes careful. Any public statement would emphasize scale and time. Nothing is approaching in the human sense. Nothing is coming for Earth. Language matters when gravity is involved. Inside the data, however, something becomes clearer. Whatever this object is, it isn't moving randomly. Its trajectory has structure. It obeys galactic dynamics. It has a past, and it will have a future. Understanding that path becomes the next priority. Because distance tells you where something is, but trajectory tells you whether it will stay. And as scientists refine these estimates, A deeper, more personal question begins to form beneath the math. Not whether Earth will survive, but how living under such knowledge might quietly change the way humanity thinks about time itself. Once distance is constrained and trajectory begins to take shape, the conversation shifts from detection to possibility. Not possibility in the cinematic sense, but in the sober language of scenarios. What happens depends not on what the object is, that part is mostly settled, but on how close it will come and how long its influence will linger. Astrophysicists don't ask whether a black hole is dangerous in general. They ask under what conditions gravity becomes disruptive. Distance matters more than identity. A black hole far enough away is just another mass in the galaxy. One that comes closer enters a different category entirely. In simulations, the first scenario explored is always the most conservative. The object passes through the outermost fringes of the sun's gravitational influence, disturbing little more than distant debris. In this case, the solar system barely notices. Data records a slow rise and fall of anomalies, then a return to baseline over centuries. This outcome is statistically the most likely. Space is vast. Close encounters are rare. Even something passing near in astronomical terms may still be trillions of kilometers away. Gravity fades gently with distance, and most of the system remains untouched. A second scenario considers a closer flyby, still not threatening, but influential. Here, long-period comets become more common. The Oort cloud is stirred more noticeably. Inner planets remain stable, but the outskirts of the system carry a memory of the encounter for millions of years. These are the kinds of events that shape cosmic history quietly. No extinction, no collapse, just a reshuffling of trajectories that echoes long after the visitor is gone. Astronomers believe similar encounters have already happened many times in Earth's past. Then comes the scenario that receives the most attention. Not because it's likely, Bess, but because it's instructive. A black hole passing within a few thousand astronomical units, close enough to measurably affect planetary orbits over long timescales. Even here, the word close is misleading. Thousands of astronomical units still place the object far beyond Neptune. No planet is ripped away. No orbits cross catastrophically. But eccentricities grow. Long-term stability becomes something to monitor rather than assume. Simulations show that in this case, Earth's orbit might change shape slightly, not enough to eject it or plunge it inward, but enough to alter climate patterns over geological time. Ice ages could deepen, warm periods could stretch. Life adapts, as it always has. What's striking is how slowly these changes unfold. A human lifetime passes without obvious consequence. A civilization might rise and fall, without ever knowing the reason seasons drifted subtly over thousands of years. Scientists pay close attention to resonance effects in these scenarios. When orbital periods align in certain ratios, small influences can amplify. Jupiter, already a dominant gravitational player, becomes a key intermediary. Its response matters as much as the black hole's proximity. This turns the solar system into a network, not a set of isolated objects. Every planet responds not only to the intruder, but to each other. The black hole doesn't act alone. It perturbs the choreography, and the dancers respond in complex ways. None of this suggests sudden catastrophe. That's the hardest idea for people outside science to accept. Extreme objects do not produce extreme outcomes by default. Physics is conditional, not emotional. Another scenario examines capture, not of Earth, but of the black hole itself. Could it become loosely bound to the sun, entering a long, distant orbit? Simulations suggest this is possible, but rare. It would require a precise exchange of energy with the galactic environment. If that happened, the black hole would become a permanent distant companion, invisible, silent, yet influential. A reminder that the solar system is not isolated, but embedded in a living galaxy. In this case, humanity would live under a slightly altered sky indefinitely, not one of danger but of awareness. A system once assumed static, now known to be dynamic. What's fascinating is how little changes on the surface of daily life in all these scenarios. Gravity reshapes futures, not mornings. It writes history in slow ink. The realization that even extreme cosmic events respect timescales far beyond panic is quietly comforting. The universe does not rush endings. It negotiates them. This part of the analysis often produces an emotional shift among researchers. Fear gives way to humility. The question stops being, "Are we in danger?" and becomes, "How stable was stability ever meant to be?" Understanding these scenarios reframes Earth's story, not as fragile, but as adaptable, not as central, but as resilient within changing conditions. And once proximity is understood as influence rather than threat, attention turns naturally to a deeper layer of consequence, not physical survival, but how awareness of such vast timescales changes human perspective itself. Because the most significant impact of a nearby black hole may not be gravitational at all, but psychological. Knowledge doesn't arrive as a shockwave, it settles. It sinks in slowly, altering how familiar ideas feel rather than replacing them outright. Once the presence of something massive and unseen becomes accepted, not as a threat, but as a condition, humanity begins doing what it always does best, adapting its sense of meaning. The first shift isn't fear, it's time. Suddenly, conversations stretch further into the future, not decades, but centuries. Not election cycles, but orbital ones. A nearby black hole reframes what long-term means, not by urgency, but by scale. Astronomy has done this before. When Earth stopped being the center of the universe, daily life didn't collapse. When evolution challenged fixed ideas of origin, society didn't end. Perspective widened. That's the pattern here, too. What changes is the mental horizon. Events are no longer isolated to human lifespans. Climate, geology, orbital mechanics. These become part of a shared narrative about continuity rather than crisis. The black hole doesn't loom. It contextualizes. Scientists, in particular, are accustomed to living with slow truths. Stellar evolution unfolds over billions of years. Galaxies collide over hundreds of millions. Adding another long-scale process to the list doesn't overwhelm, it integrates. Outside research circles, language shifts more gradually. Media learns to describe distance without drama. Teachers explain gravity with a little more humility. Students grow up knowing that the solar system is not static, but responsive. There's something quietly grounding about that idea. Stability becomes a process, not a promise. The universe isn't fragile, but flexible. Earth's story isn't written on a fixed stage, but on a moving platform. Culturally, this knowledge doesn't inspire panic bunkers or countdowns. It inspires patience, planning, a renewed respect for slow systems that outlast individual lives. Human psychology is surprisingly good at absorbing vastness when it's not framed as doom. A black hole that won't arrive, won't collide, won't consume us, but will influence over time, becomes a lesson rather than a menace. Philosophers revisit old questions with new data. What does permanent mean in a universe where even planetary systems evolve? What does responsibility look like when consequences unfold over millennia? The answers aren't dramatic, they're quiet adjustments. A deeper appreciation for continuity. That subtle erosion of the illusion that everything important must happen quickly. Art reflects this shift too, not with explosions, but with emptiness, with slow motion, with stories that stretch beyond protagonists' lifetimes. The cosmos becomes a backdrop not for heroism, but for humility. There's comfort in realizing that the universe does not single us out for destruction. It treats Earth the way it treats everything else, as a participant in ongoing dynamics, not a target. This understanding also softens existential anxiety. If even black holes obey patience, then urgency becomes a human construct rather than a cosmic one. The universe isn't rushing us toward an end. Awareness of deep time often produces a strange calm. Worries shrink. Personal timelines feel less oppressive. The future becomes something shared with generations yet unborn. That doesn't make individual lives meaningless. It reframes them as chapters rather than conclusions. Moments gain value precisely because they're brief within something enduring. In this light, a nearby black hole becomes less a symbol of danger and more a reminder. Existence is dynamic but not hostile. Change is constant but rarely abrupt. Humanity has always lived under influences it cannot see. Gravity, radiation, time itself. Naming one more doesn't fundamentally alter that condition. It simply adds clarity. And clarity, when paired with patience, tends to reduce fear rather than amplify it. As the idea settles, attention naturally drifts inward again, not to panic or preparation, but to reflection. To the quiet realization that knowing something vast and slow is different from fearing something fast and unknown, which brings the journey closer to where it began. Not in space, but in the private experience of listening, resting, and allowing the universe to be large without demanding anything in return. Fear thrives in ambiguity. Physics does not. Once the emotional weight of a black hole fades into familiarity, a more grounded question takes its place. Under what exact conditions would a black hole near Earth become genuinely dangerous? Not symbolically, not philosophically, physically. The answer is narrower than most people expect. The first misconception to dissolve is suction. Black holes do not pull harder than other objects of the same mass. Replace the Sun with a black hole of equal mass, and Earth would continue orbiting as it always has. No sudden spiral inward, no invisible vacuum reaching across space. Gravity cares about mass, not mystique. Real danger begins only when proximity crosses very specific thresholds. Tidal forces, not gravity itself, are what tear things apart. These forces arise from differences in gravitational pull across an object. When one side feels significantly more pull than the other, structure begins to fail. For Earth to experience destructive tidal effects from a stellar mass black hole, that object would need to come astonishingly close, closer than the distance between Earth and the Moon. At that point, the planet's crust would stretch, fracture, and heat rapidly. Oceans would rise catastrophically. But such a trajectory is not just unlikely. It borders on the absurd within known galactic dynamics. Black holes are compact, but space is vast. The probability of one passing within lunar distance of Earth is so low that it effectively vanishes over the lifetime of the universe. This is not reassurance by optimism. It's reassurance by statistics. Even if such an encounter was somehow engineered, warning would not come late. Orbital disruption would escalate dramatically, long before tides reach destructive levels. Planets would deviate clearly. The Moon's orbit would distort visibly. This is not a silent failure mode. Another feared scenario involves accretion, the black hole feeding on Earth's matter. This too requires proximity that defies realism. Accretion disks form when matter falls in with angular momentum. heating through friction. Earth would not quietly donate itself. It would have to be captured deeply within the black hole's gravitational well first. At distances where Earth remains intact, accretion rates are effectively zero. Space is sparse. Black holes starve more often than they feed. Most spend billions of years barely interacting with anything at all. Radiation is another concern, often exaggerated. Black holes do not emit radiation unless actively accreting. Hawking radiation exists, but for stellar mass black holes, it is unimaginably weak, far less than the cosmic microwave background that already bathes Earth. In fact, Earth is constantly exposed to far more energetic phenomena without consequence. Supernovae have occurred nearby in cosmic history. Gamma-ray bursts have swept past regions of the galaxy. The planet endured. Life adapted. The true danger zone is narrow, slow to approach, and loud in its signals. It requires distances so small and effects so strong that no subtlety remains. Physics becomes obvious when thresholds are crossed. This is an important distinction. Many cosmic threats are not stealthy. They are dramatic long before they are lethal. A black hole does not sneak up at catastrophic distance. It announces itself through broken orbits, violent tides, and unmistakable distortion. Understanding this changes the emotional framing entirely. The universe is not hiding traps behind calm facades. It escalates proportionally. Danger has a signature. The most realistic impacts of a nearby black hole are indirect and long-term. Increased comet influx, slight orbital reshaping, changes that matter to climate over tens of thousands of years, not to individuals over decades. That doesn't make them trivial. It makes them manageable. Humanity already studies and plans for processes unfolding over millennia: orbital cycles, axial tilt variations, solar revolution. A black hole's influence would join that category. The lesson here is not that nothing matters. It's that context matters. Physics offers boundaries. Fear dissolves when those boundaries are understood. There's something stabilizing about that realization. Even the most extreme objects in the universe obey rules. They don't improvise destruction. They don't act with intent. They follow gradients, equations, and limits. Once those limits are clear, imagination loses its grip on catastrophe. What remains is curiosity and a kind of sober respect for scale. The black hole stops being a monster and becomes what it always was: a region of space-time behaving exactly as predicted under extreme conditions. And when that understanding settles in, another realization follows naturally: that the most profound outcome of this entire scenario isn't physical danger at all, but perspective. Because knowing precisely where danger begins also tells you where it does not. And that leaves a surprising amount of room for calm. Somewhere along the way, the idea of a black hole near Earth stops feeling like an emergency and starts feeling like a lesson in scale. Not because the object becomes less strange, but because you begin to understand the rules it must obey. Gravity is powerful, yes, but it is also predictable. It doesn't improvise. It doesn't lunge. It accumulates its effects patiently, like a slow tide that reshapes a coastline without ever shouting its intentions. If you've been picturing a black hole as a cosmic predator, this is the moment the story gently corrects that image. A black hole is not a creature with appetite. It is a region of space-time where mass is concentrated so tightly that escape becomes impossible. That's all. The rest, fear, drama, inevitability, is something humans paint on top when we don't yet understand the distance between extreme and immediate. The most stabilizing truth is simple. Mass matters more than mystique. A black hole with the mass of the sun behaves gravitationally like the sun at the same distance. It doesn't pull harder. It pulls the same What changes near a black hole is not the law of gravity, but how sharply space-time is curved when you get very close, close enough that tidal forces become meaningful. And tidal forces are the real boundary between interesting and dangerous. They are not about gravity's overall pull, they are about differences in pull across a body. If one side of an object is tugged much more strongly than the other, structure begins to fail. This is why a black hole can be harmless at one distance and catastrophic at another. Not because the black hole changed, but because geometry did. It helps to picture it like stretching a rubber sheet. Far away from a heavy object, the sheet slopes gently. Objects roll along predictable curves, but near the weight, the sheet steepens, and the same rolling motion can become unstable. The transition between gentle slope and steep funnel is where the story changes tone, and physics becomes less forgiving. What makes this scenario soothing rather than terrifying is that those steep, catastrophic distances are absurdly small compared to the scale of space. For Earth to be torn by a stellar mass black hole's tides, the encounter would have to be unimaginably close, closer than the Moon. That isn't near in space terms. That is practically a collision of trajectories, a coincidence so rare it becomes less a prediction and more a thought experiment. So most realistic outcomes live in the quieter range, subtle orbital adjustments, long-term perturbations, shifting probabilities rather than certain doom. A black hole passing in the distant outskirts of the solar system changes the choreography gently. It doesn't smash the stage. It rearranges the music's tempo, small changes in eccentricity, procession and resonance that unfold over centuries and millennia, like slow weather patterns. This is where your mind can relax into the pace of the universe. Nothing in this story wants to happen quickly. Even the warning signs arrive as small disagreements in data, stars slightly displaced, clocks slightly out of sync, orbit predictions needing slightly larger corrections. The cosmos doesn't flip from calm to chaos in a day. It ramps, it layers, it accumulates. And you don't have to carry all of that accumulation consciously. Let it be like a distant hum outside a window, present, not demanding. Your body still understands the local world, the weight of the blanket, the softness of the pillow. To notice these slow shifts, atomic clocks, laser ranging, astrometric catalogs, spacecraft navigation networks, none of them exist to fight the universe. They exist to listen. This scenario becomes less about helplessness and more about comprehension. Even subtle cosmic influences can be measured, modeled, and placed inside boundaries of meaning. In a way, the black hole is not the main character. The main character is time. Time is what turns a massive object into a gentle influence rather than an instant catastrophe. Time is what gives science room to notice patterns, room to refine models, room to correct mistakes. Time is what lets a frightening idea soften into a knowable one. If you zoom out far enough, this is how the galaxy behaves all the time. Stars pass near each other, clouds are stirred, orbits slowly evolve. The Milky Way is not a static museum. It's a living environment with drifting remnants, quiet collisions, and gravitational conversations lasting longer than civilizations. And the solar system is not separate from that environment. It is embedded in it like a boat in an ocean current. Most days the current feels invisible, because the boat moves with it. Only when you measure carefully do you realize that motion is shared, that stability is relative, and that nothing is truly isolated. This doesn't make Earth fragile. It makes Earth adaptive. It has survived shifts in solar brightness, Changes in atmospheric composition, impacts, ice ages, supervolcanoes, magnetic wanderings, and long orbital cycles. The planet is not a porcelain ornament. It is a resilient system that can absorb gradual change and keep going. The comfort here is not denial, it's calibration. Fear often assumes the universe is out to surprise you violently. Physics suggests the opposite. When danger exists, it announces itself in escalating signals long before thresholds are crossed. When influence exists, it spreads softly, giving you distance to understand what's happening and time to place it in perspective. So the story you're listening to becomes a kind of flow therapy for the imagination. Not motivational, not sentimental, just grounding. The black hole becomes less a monster and more a demonstration that even extreme conditions can be mapped. Mystery remains, but panic is no longer required. And as your mind settles into that calmer frame, notice what happens inside your body. Your shoulders might loosen without permission. Your jaw might unclench. Your thoughts might become less sharp-edged. That's the strange gift of scale. When the universe becomes huge, the urgency of small worries often shrinks into something manageable. If sleep arrives mid-sentence, let it. There's no prize for finishing the chapter. The entire arc of this video is built for drifting. Your attention can float in and out like a satellite passing through shadow, returning to light when it wants to, resting when it needs to. Still, there are layers of this scenario that are worth lingering in, not because they raise stakes, but because they deepen texture. The really interesting effects are often the ones that don't threaten life at all, changes that only show up over thousands of years, in the edges of the solar system, in patterns that look like coincidence until you widen your view. And that's where the path leads next, to the slow consequences that make the universe feel more alive, not more hostile. The kind of consequences that reveal how long gravity can hold a conversation without ever raising its voice. So tonight, the story doesn't sprint toward an ending. It narrows gently into quieter questions, questions that feel almost personal, because they touch the way you perceive time, patience, and the difference between danger and uncertainty. Let your breathing stay steady while the universe stays steady too, and allow the next layer to arrive the way the cosmos prefers. Gradually, softly, with no need for urgency at all. Some effects are too quiet to belong to danger, but too persistent to be ignored. They don't announce themselves through disruption. They leave fingerprints instead, faint, cumulative marks that only become visible when you stop thinking in years and start thinking in eras. This is where gravity does its most patient work. When a massive object passes through a region of space, it doesn't just influence what is nearby in that moment. It changes probabilities. Paths that were once unlikely become slightly more common. Others fade. Over thousands of years, those small statistical shifts begin to shape outcomes in ways that feel intentional, even though they are not. In the outer reaches of the solar system, this kind of influence accumulates quietly. Objects there move slowly, loosely bound, easily persuaded by subtle changes in gravitational background. A passing black hole would leave behind a gentle distortion, not a scar, but a bias. Certain orbits become favored, certain trajectories become rarer. From Earth's perspective, this might eventually appear as patterns that seem coincidental at first, comets arriving from similar regions of the sky, long-period visitors appearing more often than models once predicted. Nothing dramatic, just enough repetition to make coincidence feel insufficient as an explanation. Astronomers already work with these kinds of clues. They reconstruct past events not by seeing them, but by reading distributions, angles, velocities, energies, Space keeps records, but they are written in statistics rather than images. The most interesting part is how long these fingerprints last. Long after the black hole has moved on, its influence remains embedded in the architecture of motion. Orbits remember. Debris fields remember. Even when the cause is gone, the effect continues to unfold. This is not unique to black holes. Passing stars do the same thing on smaller scales. Galactic tides reshape systems over billions of years. The universe is full of long echoes that outlive their sources. What makes a black hole different is not aggression, but depth. Its gravitational well is steep, and even at distance, it can leave a lasting bias. Not enough to destabilize everything, just enough to matter over time. Earth itself has lived through these kinds of slow influences before. Its orbital parameters, eccentricity, tilt, precession, change gradually due to interactions with other planets. These cycles shape ice ages, climate rhythms, and long-term habitability without ever feeling urgent. A distant black hole would simply add another layer to that slow conversation. Another voice speaking softly, too low to hear day to day, but persistent enough to shape long outcomes. You don't feel these changes because your nervous system is tuned to immediacy. It notices danger, not drift, but the planet responds to drift constantly. It has no need for alarm. It adjusts as physics allows. There's something calming in realizing that the most meaningful changes in the universe often arrive without sensation. No warning bells, no thresholds crossed, just a gradual leaning of probability in one direction instead of another. Scientists studying long-term dynamics often describe this as living inside uncertainty without urgency. The system is stable, but not fixed, predictable, but not frozen. That balance is where most of reality exists. This perspective changes how you relate to the idea of influence. Influence does not have to be forceful to be real. It doesn't need to be felt to be effective. Gravity, at its most powerful, is often almost invisible. As your breathing remains steady, imagine time itself as the medium through which these changes travel. Not rushing, not stopping, simply carrying small deviations forward until they become history. The universe doesn't erase its past, it folds it forward. Every interaction leaves a trace, however faint, and those traces layer until the present becomes textured with ancient causes. In that sense, a nearby black hole wouldn't be an interruption. It would be an addition, another thread woven into an already complex fabric of motion. Nothing about this demands action, nothing asks for response. It simply invites awareness of how deep time really works. And once you begin to sense that depth, attention naturally drifts outward again, not toward fear, but toward the environment that makes such encounters possible in the first place. Because these fingerprints don't exist in isolation. They belong to a galaxy that is constantly moving, reshaping itself and carrying its contents along vast, invisible currents. And that larger environment has its own quiet logic, one that extends far beyond any single system drifting within it. It's easy to imagine the galaxy as a static backdrop, a painted dome of stars that exists only to be looked at. In reality, the Milky Way is in constant motion. Everything within it drifts, circles, oscillates, and migrates, carried by gravitational currents that unfold over hundreds of millions of years. The solar system is not parked in space. It is traveling through a dynamic landscape. Stars orbit the galactic center at different speeds, depending on their distance, creating shear, tides, and density waves that ripple through the disk. These waves, compressed gas, triggered star formation, and slowly rearrange stellar neighborhoods. Nothing stays in the same company forever. Proximity is temporary on cosmic timescales. Black holes are part of this population. most formed from massive stars that lived briefly and collapsed long ago. This wandering is not rare. Astronomers estimate that the Milky Way may contain tens of millions of stellar mass black holes. The vast majority never come near anything of interest. Space is simply too large, but movement ensures that encounters, however distant, eventually occur. The solar system itself oscillates up and down through the galactic plane, completing a vertical cycle roughly every 60 million years. During these passages, it encounters regions of slightly different density. More gas, more stars, more remnants. Each passage subtly alters the gravitational background. These motions leave signatures. Some researchers have noticed correlations between these galactic cycles and long-term patterns in Earth's geological record. Not causes, not triggers, correlations. Enough to suggest that the solar system's environment matters more than we once assumed. In this context, a nearby black hole is not an invader. It is a fellow traveler passing through the same galactic currents. Its influence is part of a broader gravitational weather system that shapes trajectories over deep time. The idea of near becomes relative here. Near on a galactic scale can still mean trillions of kilometers away. Influence spreads softly, like pressure in a fluid, adjusting flows rather than breaking structures. Astrophysicists model the galaxy as a living system, not a clockwork. Spiral arms are not rigid structures. They are density patterns that move through stars like traffic waves. Objects enter them, linger and leave. Black holes participate in this dance without special privilege. When the solar system passes through denser regions, the probability of gravitational encounters rises slightly. Not catastrophically, just enough to add texture to long-term motion. Encounters that would be impossible in empty space become merely unlikely. This perspective dissolves the idea of isolation. Earth is not shielded by emptiness. It is embedded in a flow. That flow is slow, lawful, and remarkably forgiving. Understanding this environment reframes concern into curiosity. The question shifts from what could happen to us to how often has this already happened, quietly, without notice. Evidence suggests the answer may be many times. The solar system's distant reservoirs have been reshaped repeatedly. Passing stars have stirred comet clouds. Galactic tides have nudged orbits. Life persisted through all of it. The galaxy does not single out planets for attention. It treats systems statistically, not personally. That statistical nature is what makes it stable. Extreme outcomes are diluted by vastness. This realization has a calming effect. When danger is distributed across enormous scales, immediacy evaporates. What remains is pattern, not threat. You can think of the galaxy as a slow river carrying everything within it. Some currents are stronger, some weaker. Objects drift closer than apart. Most interactions are glancing, leaving only gentle ripples behind. A black hole passing within influence range of the solar system fits neatly into this picture. It is neither omen nor anomaly. It is a consequence of motion in a crowded gravitational field. Once you see the Milky Way this way, stillness becomes the illusion. Change is the baseline. Stability is something achieved dynamically, not something granted forever. And yet, despite all this motion, local experience remains calm. Days pass, seasons repeat. Life unfolds on a scale where galactic dynamics feel abstract. That separation of scales is a gift. The universe allows small, fragile processes to exist inside vast, indifferent ones without constant interference. that coexistence is not accidental. It's built into the math. As this broader view settles, attention naturally drifts backward in time, not toward prediction, but toward memory, toward the question of whether traces of similar passages might already be written into Earth's deep history. Those traces, if they exist, would be subtle, easy to miss, waiting quietly in data rather than in stories. And that is where the path leads next, into echoes left behind long before anyone was around to notice them. Long before humans learned to read the sky, the Earth was already recording events in ways no one would recognize for millions of years. Not as stories, not as memories, but as subtle rearrangements in motion, chemistry, and probability. The planet doesn't document its past loudly. It buries it slowly, layer by layer, beneath oceans, ice, sediment, and time itself. When astronomers ask whether Earth has experienced distant gravitational encounters before, they aren't looking for smoking guns. They're looking for statistical fingerprints, patterns that don't belong to internal processes alone, slightly altered distributions of impacts, long-term cycles that don't quite align with known planetary mechanics. Anomalies that only appear when data sets span tens or hundreds of millions of years. One place these echoes may hide is in the history of comet influx. Earth's impact record is not uniform. There are periods where long-period comets appear more frequently, followed by long quiet stretches. Some of this can be explained by internal solar system dynamics. Some cannot be explained so cleanly. The What cloud, that distant halo of icy debris surrounding the solar system, is extremely sensitive to external influence. Passing stars are known to disturb it. Galactic tides stretch it. A massive object drifting nearby would not shatter it, but it could bias it, sending slightly more debris inward over extended timescales. From the surface of Earth, this wouldn't look like a disaster. It would look like history unfolding normally. The occasional impacts, long quiet eras, life adapting, diversifying, sometimes struggling, sometimes flourishing. The cause would never be obvious to the organisms living through it. Geologists reading Earth's strata today don't see black hole past here. They see isotope ratios, shocked minerals, iridium layers, tiny chemical irregularities that suggest something arrived from beyond without ever revealing why. This is where science becomes almost archaeological. Researchers cross-reference crater ages with orbital models, galactic motion, and stellar encounter reconstructions. They don't expect certainty. They look for coherence, different lines of evidence leaning in the same direction. What makes this difficult is that Earth is noisy. Volcanoes, tectonics, climate shifts, biological feedback loops, all of these leave strong signatures that can drown out faint gravitational echoes. Separating cosmic influence from terrestrial chaos is painstaking work. Yet sometimes patterns persist, even after accounting for all known causes. Not patterns that scream explanation, but ones that quietly resist dismissal. Clusters of events that align better with external perturbation than with chance alone. It's important to say this clearly, none of this implies doom. Earth has endured everything recorded in its rocks. Whatever distant influences may have nudged probabilities in the past, they did not erase life. They became part of its story. In fact, some researchers argue that mild external perturbations may even contribute to long-term resilience. By preventing systems from becoming too static, they introduce variability. And variability is something life is remarkably good at navigating. What's unsettling is not danger, but humility. The realization that some chapters of Earth's history may have been shaped by influences no one present could ever perceive. No warning, no sign, just slow consequence. Imagine living inside a system where causes and effects are separated by millions of years, where nothing feels different day to day, yet the statistical future bends ever so slightly in one direction. That is how deep time physics operates. This reframes the idea of event. Not everything important happens suddenly. Some of the most influential moments in Earth's past may have unfolded without any organism ever noticing that something had changed. From that perspective, a nearby black hole in the distant past would not be an interruption. It would be another quiet nudge in a universe full of nudges, one more influence among many shaping probability rather than certainty. The planet doesn't react emotionally to these influences. It absorbs them. Adjusts, continues. Oceans still cycle. Atmospheres still evolve. Life keeps experimenting. What humans call normal is just a narrow slice of an ongoing process. Stability is not the absence of influence. It's the ability to remain coherent while influences accumulate. That idea can feel unsettling at first, but it doesn't need to be. It means Earth's history is richer, more interconnected, and more robust than a simple cause and effect narrative. Even now, traces of ancient interactions may still be unfolding, not as crises, but as gentle statistical biases working their way forward through time. Nothing about this demands fear. If anything, it invites patience. The universe has been interacting with Earth far longer than humans have been able to wonder about it. And that raises a quieter, deeper question, not about what might happen next, but about how much of what already happened was shaped by influences that never announced themselves. That question doesn't have a sharp answer. It has a texture, one that rewards stillness more than urgency. As attention drifts forward again, away from ancient echoes and back toward the present, something becomes clear. Understanding doesn't always arrive as revelation. Sometimes it arrives as acceptance of how much happens below the threshold of awareness, and from there, the path naturally turns toward the limits of prediction itself, toward the realization that some futures cannot be forecast cleanly, no matter how carefully you listen. At some point, every scientific investigation reaches a boundary that isn't marked by ignorance, but by complexity. Not a wall that says, we don't know, but a horizon that says, we can't know this precisely forever. When gravity involves many bodies interacting over immense spans of time, prediction slowly loses its sharp edges. This isn't a failure of science, it's a property of dynamical systems. When multiple objects influence one another continuously, tiny uncertainties grow, not linearly, but exponentially. A minuscule error in position or velocity today can produce vastly different outcomes millions of years later. This behavior is known as chaos. Though not in the dramatic sense, chaotic systems are not random. They are lawful, deterministic, and still fundamentally unpredictable beyond certain timescales. The solar system itself contains regions of this quiet chaos. Planetary orbits feel stable because they are stable on human timescales. But simulations show that over hundreds of millions of years, even small gravitational nudges can rearrange orbital resonances in ways that no model can forecast exactly. Add a distant black hole into this system, and you don't introduce madness, you introduce sensitivity. The equations remain the same. What changes is how sharply outcomes diverge when you roll time forward. Astrophysicists don't run a single simulation for scenarios like this. They run thousands, tens of thousands. Each one starts with nearly identical initial conditions, differing by less than measurement error. Over time, the futures fan out. Some futures remain calm indefinitely. Others drift into slightly altered configurations. A few wander into instability, long after anything resembling danger could be observed or acted upon. None of them exploded suddenly. They diverge gradually. This is why long-term forecasts are always probabilistic. Scientists speak in distributions, not certainties. They ask which outcomes are more likely, not which is guaranteed. This frustrates people who want clean answers. Will it happen or not is often the wrong question. The correct question is, how likely is each possible future, and how does that likelihood change over time? In this framework, a nearby black hole doesn't create a single destiny. It widens the tree of possibilities. Some branches remain familiar. Others bend subtly away from what would have happened otherwise. Importantly, this uncertainty does not scale with fear. It scales with time. The farther you look into the future, the softer predictions become, regardless of whether a black hole exists. Earth already lives inside this uncertainty. Long-term climate cycles, orbital variations, and tectonic evolution are all predictable only within ranges. Precision belongs to the near future. The deep future belongs to probability. What changes emotionally when people realize this is subtle but profound? The idea of control dissolves. In its place emerges stewardship, not of outcomes, but of conditions. Science becomes less about domination and more about navigation. You can't steer the galaxy, but you can understand the currents well enough to avoid illusion. This is where the presence of a black hole stops being central. The real lesson is that the universe was never fully predictable to begin with. The black hole merely reveals that truth more clearly. There is something oddly comforting about this limit. It means the universe is not a rigid script. It is an evolving process where certainty fades gracefully rather than collapsing suddenly. Uncertainty here is not danger. It is breathing room. It allows for adaptation, resilience, and surprise without catastrophe. Humans tend to fear what they cannot forecast. But life has always existed beyond forecast. Evolution itself is an exploration of possibility space, not a march toward a predetermined endpoint. Seen this way, the inability to predict everything far into the future becomes a feature, not a flaw. It prevents stagnation. It keeps systems flexible. A black hole passing near the solar system does not rob humanity of certainty. It reminds humanity that certainty was never infinite. And that reminder, while initially unsettling, often leads to a quieter acceptance that understanding the rules matters more than predicting every outcome. Once that acceptance settles in, the story naturally turns toward its emotional landing, not toward fear of what cannot be known, but toward peace with what does not need to be known. Because if the universe itself lives comfortably with uncertainty, perhaps there is no reason you shouldn't as well. And from that realization, the final movement of this journey begins, not outward into space, but inward, toward rest. When everything is finally laid out, the distances, the timescales, the probabilities, the limits of prediction, something unexpected happens. The universe begins to feel less threatening, not because it became smaller, but because it became legible. Not fully understood, but coherent, governed by rules that don't shift depending on fear. A black hole, once imagined as a symbol of chaos, reveals itself as one of the most obedient objects in existence. It follows equations without exception. It curves space-time exactly as mass demands. It neither accelerates nor hesitates without cause. In a strange way, it is more predictable than many familiar things on Earth. This is the deeper comfort hiding beneath the science. The universe is extreme, but it is not impulsive. It does not change its mind. It does not wake up in a different mood. Even its most violent phenomena are expressions of consistency, not randomness. Living inside such a universe means that uncertainty has boundaries. You may not know outcomes far into the future, but you know the rules governing how those outcomes emerge. That knowledge is stabilizing. It replaces dread with orientation. Consider how many invisible forces already shape your existence without harm. Gravity holds you gently to the surface. Time moves in one direction without negotiation. Radiation passes through your body constantly without consequence. Stability has always depended on things you never feel. A nearby black hole does not rewrite that condition. It reinforces it. It becomes another reminder that safety does not require stillness. It requires balance within motion. This realization changes how scale feels. Immensity stops being overwhelming and becomes spacious. The galaxy becomes less like a threat and more like an environment. One with weather patterns, currents, and long-term rhythms that rarely intrude on the small spaces where life unfolds. The mind relaxes when it stops expecting catastrophe from magnitude alone. Large does not mean hostile. Ancient does not mean cruel. Unknown does not mean imminent. What remains after fear drains away is a quiet respect. A recognition that the universe is not arranged for comfort, but it is arranged for continuity. Things persist. Systems adapt. Order reemerges again and again. In that context, your presence feels less fragile. You are not balanced on the edge of disaster. You are embedded in layers of resilience built by physics itself. Even change, when it arrives gradually enough to be understood, responded to, and absorbed. The universe does not rush endings. It allows time for awareness to catch up. This is why the thought of sleeping beneath a sky shaped by black holes no longer feels unsettling. It feels honest. Reality was always shaped this way. You're simply more aware of it now. Awareness does not demand action. It does not require vigilance. It can coexist with rest. And rest in a lawful universe is not denial. It is alignment. As attention softens, the details of gravity, motion, and probability fade into background texture, not gone, just no longer demanding analysis. Understanding has done its work. What's left is the sense that being here, in this moment, is not at odds with the vastness around you. The small and the immense are not in competition. They coexist, and that coexistence is steady enough to lean on. The question that opened this journey was never really about destruction. It was about proximity, about what changes when something unimaginably dense comes near, and whether that nearness should be feared. After walking through gravity, time, matter, uncertainty, and scale, the answer feels different than it did at the beginning. A black hole near Earth would not arrive as a sudden ending. It would announce itself slowly, through patterns, through patience, through math that refuses to panic. Long before danger, there would be understanding. Long before understanding, there would be time. The universe does not hide its intentions. It reveals them in gradients, in curves, in quiet deviations that only grow meaningful when observed with care. Along the way, you've passed through laboratories, observatories, ancient rocks, distant clouds of debris, and equations that stretch farther than intuition. None of them demanded urgency. All of them rewarded attention. And now, attention is no longer needed. What matters has already settled. The cosmos remains large. Life remains possible. Rest remains appropriate. If you fell asleep somewhere along the way, that's exactly how this was meant to work. The universe does not require witnesses for its truths to remain true. And if you're still listening, still aware of the quiet around you, there's something gently comforting in knowing that other people, in other rooms under other skies, are listening to the same story at different hours of the night. If you feel like it, you can leave a comment saying where you are and what time it is there. It's a small reminder that even across a spinning planet, moments can line up. If nights like this, calm, curious, unhurried, feel useful to you, you're welcome to return again. Not out of obligation, but because the questions will still be here, waiting patiently. For now, nothing needs solving. Nothing needs guarding. The universe continues its motion. Gravity continues its accounting. Time continues forward without asking for permission, and you can let your mind do what it does best when it feels safe enough. Slow down, drift, and rest, knowing that even under the influence of the most extreme objects in existence, the night remains quiet.